Hello everyone, my name is Bohdan Didenko. I am deep learning engineer at WebSpellChecker. Welcome to our presentation on 2023 UNLP shared task focusing on grammatical error correction for the Ukrainian language. Today I am excited to introduce our innovative sequence-to-edits architecture called RedPenNet. Now, few words about company. WebSpellChecker LLC is Ukrainian-based company registered in 2016. While the product history goes back much further, starting in 1999. WebSpellChecker provides a portfolio of multi-language sentence check solutions for dev companies, businesses, and individuals, available as cloud-based and on-premise products. The development of RedPenNet architecture was an iterative process, involving numerous of attempts and experiments to refine our approach. Let me share with you our journey through the dawn of the fine-tuning era, the architecture we employed for BIA 2019 shared task, the insight we gained from the outcomes, and how it all led us to develop RedPenNet, which we successfully utilized in UNLP 2023 shared task. Our journey on developing our own neural grammatical error correction engine began in mid-2018. It's an important year in the NLP field. Such models as ELMO, GPT-1, and BERT were released during this year. From this period, pre-training and fine-tuning era has begun. The NLP industry quickly shifted to fine-tuning these models for a wide range of downstream tasks, including name entity recognition, question answering, summarization, and grammatical error correction. Naturally, we also wanted to leverage cutting-edge technology in our research to create the GC engine. As a result, shortly after BERT's public release, we submit a small pull request to BERT repository, suggesting to convert IDs back into tokens, as we wanted to explore the potential of using BERT for GC. At the time when we were actively experimenting with the BERT for GC task, we came across the BIA 2019 shared task, which focused on developing a grammatical errors correction solution for the English language. We devised a multi-head architecture where each distinct head was responsible for different error types. Most of the head is just trainable tagging output layer that predict edits using their own vocabularies. Audience members familiar with the field may observe some similarity between our approach for BIA 2018 and Grammarly's vector tagging model. So our approach had a unique feature for handling multi-token edits, which we call it the highlight and decode technique. We added a special highlight embedding to the encoder output at specific position determined by the range head, and utilize the combination of the decoder and autoregressive generation of correction for the highlighted token. While working on the architecture for the BIA shared task, we began to realize that the tagging approach might not be the perfect solution for the GC task. Grammatical error correction belongs to the sequence-to-edit category, where the input and output sequence are frequently similar, but the pattern isn't always consistent. Input and output sequences can have all the same tokens with no errors, or no matching tokens, and it's more close to the sequence-to-sequence task, or may only need a partial replacement of the original text. An additional challenge is the interdependence of some changes, such as paraphrasing, words or sentence parts transferring inside the sentence, or verb-tense agreement. Sometimes it's not possible to accurately predict subsequent edit without considering previous changes. From the GC perspective, sequence-to-sequence is a specific case of sequence-to-edits. What makes the transformer architecture so powerful? Its universality. Without major architecture changes for over 5 years, the transformer architecture continued to deliver top results primarily due to scaling. Moreover, we have yet not reached its theoretical limit. We wanted to come up with some similar in terms of flexibility and scalability approach for the sequence-to-edit tasks. So we arrived at the RedPenNet architecture. RedPenNet is made up to the pre-trained encoders and shallow decoders with just a few layers or even a single layer. It generates the text of edits and edits positions simultaneously. Main requirements for this model should be autoregressive model, for maintaining consistency between interrelated edits, and don't overuse computation on recreating the correct parts of the text. Let's look at how it works step by step. Get embeddings of input tokens, feed forward it through the encoder, utilize encoder output to decoder, get edit tokens from decoder outputs, and span position from the attention logits from the last decoder layers. Position prediction is just classification task with vocabulary size equal to max input length. For feedback loop, we concatenate token embeddings from the decoder vocabulary and encoder embeddings from a specific span position. Similar approach was introduced in pointer network article. And just continue after regressively generate until phase end of sequence token. After profiling the performance of the new model, we came to the conclusion that the largest amount of computational time occurs not in the layers of the decoder and not during the self-attention operation, but when obtaining the distribution of output tokens. This is due to the large size of the embedding matrix. Our experience shows that creating small task-specific binary pair vocabs significantly speed up the generation of edit tokens and doesn't increase the length of output. Let's compare RedPenNet with another sequence-to-edits solutions. The seq-to-edits approach similar in terms of prediction span position using a pointer network. And in this article, authors also predict only replacement tokens keep the correct parts of the sentence. But as we see, this architecture uses some numbers of different decoder layers connected in chain. Erroneous span detection and erroneous span correction approach also propose to predict only correction, but use two different models. First for prediction spans and second to generate corrections. Little remains highlight and decode techniques from our BIA 2019 approach. The laser tag also autoregressive generates edit, but has a restriction related to ability to generate only one replace from vocab for each position. All possible correction strings pre-computed in vocab. And finally, the first shared task on grammatical error correction for Ukrainian, conducted by Grammarly. The organizers created the UAGEC dataset and set up the CodeLab competition. Since the RedPenNet architecture can be easily adapted for different languages, we needed a minimum number of actions to take part in this task using RedPenNet to apply it to Ukrainian language. We use multi-language pre-trained model that trained on corpora that includes Ukrainian language. Pre-compute the decoder binary pair vocab. For this, using edits from UAGEC dataset with combination with list of the most frequent Ukrainian words. Generate synthetical data by back translation method and use for it Uber text corpus for Ukrainian language, and use ensembles of large and base models. As you can see, we took the third place with small difference of another readers. One of the reviewers proposed to test our approach on English benchmark, and we did it. We use the Muppet Roberta and XLNet pre-training encoders, pre-compute the decoder vocab based on W&I Lockness train edits, and pre-training on synthetical data from few public sources, and fine-tuning on combination of W&I Lockness train and C-Web dataset. If you take into account that the first place in the chart is a UAGEC system combination that just merges results of different existing approaches, we maybe can say that our approach achieved state-of-the-art result. Thank you for your attention.